Hi, welcome back to LeetCode. So in this video, I'm going to discuss LeetCode problem 3620, network recovery pathways. So you are given a directed acyclic graph of n nodes numbered from 0 to n minus 1. So this means a graph is present. This is actually directed, right? Acyclic. So that means there is no cycle in the graph. This is represented by a 2D array edges of length m, where edges I represents ui, vi, cost I. So that indicates a one-way communication from node ui to vi with the cost wi. Okay, cost I. Okay, so some nodes may be offline. Okay, you are given a boolean array online, where online I, if it is true, that means the node I is online. If it is false, that means this is offline. So they mention that node 0 and node n minus 1 are always online. Okay, so a path from 0 to n minus 1 is valid if all the intermediate nodes on the path are online. Okay, so that means like suppose we actually have some intermediate node. Okay, and this is suppose 0 and this is suppose n minus 1. So there can be this actually directed acyclic graph. So suppose there is another path, this is one path also, and this is a third path to go to the from 0 to n minus 1. So that means this path will be valid 1 1 1 to indicate that this is the path 1. So this path will be valid if all the nodes, that means this node, this node, this node, and this node also all are actually online. Okay, and the total recovery cost of all the edges on the path doesn't exceed k. So that means suppose we actually have here, we have cost 1 for this edge from 0 to this node, and this actually c2 cost 2, and here actually cost 3. Suppose actually we have given a k, so that means this path will be valid if all the nodes actually online, and total cost for this path like c1 plus c2 plus 3t, that should be less than equal to k, correct? Then this path will be counted as a valid path. Now for each valid path, define its score as the minimum edge cost along the path. So that means suppose this path is actually valid, this path they are trying to say is suppose valid, this path suppose actually valid. Okay, so that means all the four nodes actually here are online, and the cost c1 plus c2 plus c3 is less than equal to k. Okay, then what will be the score for this path? Score will be the minimum cost in the path, that means minimum of c1, c2 and c3. So for each valid path, define its score as the minimum edge cost along that path. So what is the cost actually present here in this path? C1, C2 and C3. So I have to choose the minimum one of them, right? So here for this the minimum will be something C1 or C2, C3. Now we have to return the maximum path score. The largest minimum edge cost among all valid paths. If no valid path exists, so return -1. So that means our by default answer will be -1. Now if we found any valid path, then we have to check that for this path, for this valid path, what is the minimum cost, correct? Minimum cost. Then I will compare that is actually maximum or not. Like suppose the actually multiple path actually present, suppose path 1, path 2 and this actually path 3. So for this path, what is the score? Suppose here actually score is actually SC1, here actually score is SC2, actually SC3, suppose. So then what we have to return? We have to try to maximize the score. So that means I have to ultimately choose that what is the maximum score. So that means SC1, SC2, SC3, correct? So the maximum value out of this. So that means what I have to do, our ultimate goal, that first of all find all the valid paths, then find out the score of this path, right? Score will be what? Minimum of the all the cost of the edges, right? C1, C2. Then for this path, I will actually compare with the answer, right? That this score actually is maximum or not. You will check a maximum answer, then I will actually compare, I will actually modify the answer variable, and then ultimately, after creating all the valid paths, I have to ultimately return the answer variable, correct? Got it? So let's see the example one. So what actually they're trying to say, that we actually have one edge from 0 to 1, from 0 to 1. That means this edge, the OAT is actually, the cost is 5, and another edge actually, next is from 1 to 3, the cost is 10. So that means this edge from 1 to 3, the cost is actually 10. Next, another edge from 0 to 2, the cost is actually 3. Okay. Next, from 2 to 3, this 2 to 3, the cost is actually 4. Okay. So this is actually our graph. Now let's see which actually all nodes are actually online. All are actually true, so all are actually online. Okay, so here actually k is equal to 10, right? K is equal to 10. That means, so how many actually valid path actually possible? Like ultimately we have to start from 0, and ultimately we have to try to reach to node n minus 1. So here actually n minus 1 actually ultimately 3, right? So start from here. Here actually a source and destination is this node. Now how many actually valid path actually possible here from this graph? Let's see. So this is actually one path actually is possible, this path, right? Now, so what is the condition to valid a valid path, this path? So the condition, first condition is that all the nodes in the path should be actually online. So 0 is online, 1 is also online, 3 is also online. So first condition is valid. Now next condition is that the cost of this path, the total cost, should be less than equal to k, right? So that will, first cost is 5, another cost is actually 10, less than equal to k. So that is 15 less than equal to k. Here actually value is 10. No, so this is not a valid path, correct? So this is not a valid path. This path actually not a valid. Next, try to explore this path. Is it possible to, from this path can actually go to this node 3, from 0 to 3? Okay, first I have to check that all the nodes in this path actually all are actually online or not. So 0 is online, 2 is also online, 3 is also online. Okay, next condition is that the cost or total cost in this path should be less than equal to k. So what is the total cost? That is 3, another cost is 4, so 7 less than equal to 10. Here actually k value is 10. So this is a valid path. Now what should be the score? What will be the score for this path? So I have to choose the minimum of all the cost. So 3 and 4. So the minimum cost is 3. So the score will be 3 for this path. And our answer will be initially, that I have to return, that is initially -1. Because why should I be initially using -1? Because they mentioned that if there is no valid path exists, that time I have to return -1. So that's why already initially with -1. So whenever actually found any valid path, then actually compare what is the score actually I have, this actually maximum or not. So here actually 3, this is valid path. So I'll compare that what is the maximum actually score actually I actually have till now, that is -1. So but current score is 3. So this actually maximum. So I'll actually modify this with 3. Got it? So I actually, is there any valid path actually possible after this path? No. So that's why, what is the ultimate answer actually I have 3. So that's why you can see that for this example, the output is 3. Clear? What is 3? Now, how should actually approach this problem? So first of all, what is the mention that all the nodes should be online, correct? Now first of all, what I have to do? So first of all, filter out all the offline nodes, correct? Then if I actually filter out that, then what will I have to do? So I'll actually create the modified graph. So that means, suppose we actually, the input graph actually something look like this, suppose. So this is actually the input graph, directed acyclic graph. So suppose this is actually offline. This is suppose actually offline. Okay. So that means, can I actually go through this path? No. This edge actually is not a valid. This is also not a valid, because I have to count only the online, the nodes that is online. So this path is not valid. So that's why at least one. So this edge will be also discarded. So that means the modified graph will look like this. So this is the modified graph. Got it? So this ultimately I have to check this actually what is the valid path in this graph, because I do not need to do any operation or try to calculate that what is the valid path and what is the score for that path. Then you have to check that this is actually a valid path or not. Like we can actually easily filter out the validate the first condition. That means at the beginning, if I actually remove all the nodes that are actually offline, then ultimately like in future whatever actually calculate I actually do, that will be always based on the online nodes, correct? So that's why first of all, to honor the first condition that all the nodes should be online, so that's why at the initial at the beginning actually you remove all the nodes actually offline, got it? Then actually we will actually have some modified graph, maybe. So then what to do, I will check that like what is brute force approach, what actually I can do. So our target is to maximize the score, right? Maximize the score. Now what I have to do, I actually go to what, from left to right. So right, that means our answer will be initially it will be -1, correct? Now I'll check that score 0 by using the score 0. Do we actually have a valid path with this score, with this current score? Okay, if it is valid path, then I will actually, if present, then this will be our one answer. So I'll actually modify our answer with score. Then I will actually increase our score plus. Got it? What is the brute force approach? What are you thinking? How actually I am going to think from brute force to optimize in the contest. So first of all, the brute force approach is that first of all, to validate the first condition, to honor the first condition, all at the initial phase, just filter out all the offline nodes. Then we actually have some modified graph. Then on that graph, I will check that if I want can actually have a valid path with this current score. Suppose this current score actually I am starting from 0. Current score is 0. Okay. If there is any valid path with the current score, then this is our possible answer. So I'll modify with the answer. Okay. Next, but I will not stop here. Why? Because I have to like maximize the score. So that's why I will again go for the next score. It is possible to have any valid path with this next score. Suppose what I am trying to say, is it clear? Like first of all, check that with this score 0, is it a valid path in the modified graph. So then if there is any valid path, okay, so I will modify the answer. Else or anything, I will go to the next score. I'll check that by score 1, is there any valid path? Again, I will check that. Then I will check that with the score 2, is there any valid path? In this case, I will go the next till the maximum value, like 10 to the power 9. Maximum score is possible, suppose 10 to the power 9, suppose. So it will actually take like the first of all to check each score. It will actually take big of n, because there is suppose 0 to 10 to the power 9. So it will take, I have to iterate each score. So it will be 10 to the big of n. But to check that is there a valid path or not, I have to again visit all the nodes in the graph, correct? So that's why it will take big of v in the worst case. So in the what is the time study for this approach, it will be n into v. So n is from 0 to 10 to the power, I am checking that score is possible or not, and v is the number of vertices, right? Like number of nodes, right? In the worst case, I have to visit all the vertices in the graph. So that's why it will actually almost n square, like, right? This is clear. Now how can you optimize this? You just see the observation how to optimize this here. So previously I have made many videos regarding this for this from iterative approach to how to use optimize this here. So instead of iterative search that for this particular score is possible or not, then next score, can actually use binary search here, right? I know the range because ultimately I am starting from 0 to 10 to the power 9. So I know the range. So that ultimately this is our maximum scope, right? So this is the left and this is the right. So what I have to do, I'll check that this mid, by this mid, is there any valid path? Is there any valid path? I will assume that this is the current score. Okay, so if it is valid path, then whatever this will be our answer. Answer will be modified with mid. Then what actually I should shift the left pointer and right pointer. So in this case, our goal is to maximize the score. So then actually our goal will be to shift the left pointer to here actually, because then actually it is possible that in future I may get actually a maximum answer. So that's why I will actually shift the left pointer to the mid plus 1. Else, that means if there is no valid path with the current score, then actually shift the right pointer to the mid minus 1. Why actually shift right pointer to the mid minus 1? Because if actually in the current score or the mid, using the mid score, it is not possible to get any valid path, then that means what? We have discarded some edge, because the cost is suppose greater than equals to mid, greater than equals to mid. So that's why this is not possible. So that's why our target is to take more edge in the graph. Then it may possible that we can actually get some valid path, right? So that's why that time I actually shift the right pointer to the mid minus 1. This is clear. So how we actually checking that there is any valid path or not? So that means we actually have some. So this is actually our graph. So this is suppose, okay, this is actually graph. Suppose the cost is, suppose here actually it is 2, 3, 4, 5, 6, 7. So in the binary size, suppose initially I got mid is equal to 5. Okay, and k is equal to suppose k is equal to suppose 10. Okay, suppose, let's see how actually it will work. And this is the modified graph after filtering out all the offline nodes. Okay, and this is actually the mid and this is actually the k. Okay, let's start. So I am starting from here. So this is actually 7. Okay, and what is the score? 5. So I can actually take this edge, correct? Because the cost is greater than equals to mid, right? 7 is greater than equals to 5. So if it is 4, then actually I can't take this edge to the current graph, because I have assumed that this is actually the score. So if it is smaller than mid, then this edge will not be present in the actual graph. Actual graph means in the actually we find any valid path with the current score. This, if it is present, suppose 4 is present, if I consider this 4 in the current graph, in the current path, then what will happen? Ultimately our score we are taking the minimum all of this, suppose 4, 5, 6, 7. So it will return 4, then our score will be less than 5. So that is actually true, false. So that's why I will consider only the edges that actually cost is greater than equals to mid. Then actually only I can actually consider, right, in the current path. So that's why I'll check that, okay, this is clear. Why actually I will not consider if 4 is present in the weight. Clear? Because if we add this current edge into the current path, then what will happen? I will get whatever the score actually I will get, that will be less than equal to mid, less than mid. So that actually gives us the false. This is not a valid path, right, with the current score. So that's why this path actually, this edge actually I can consider, because the 7 is greater than equals to 5. The score actually I want to actually generate. Okay, next is this edge. Can actually consider this edge 5. What is 5? Yes, this is actually greater than equals to 5. The mid actually I want. Okay, but let's one thing observe. But what is they mention that I can consider only one the path only if the total cost is less than equal to k. Here actually the total cost is 12. Less, what is the k value? K value is 10. So that's why this I have to stop here, right? Because I can't go to this node from this path by using this path. Clear? Why? I can take this edge 5, but the total cost I will get that actually exceeding the k value, right? So okay, let's say another path. Yes, this is actually another path. Yes, 6. Okay, 6 is greater than or equals to 5, I can actually take this. Okay, next is this edge. Actually I can actually take this edge. Yes, 4 is no, 4 is less than 5, so I can't take this, so I have to stop here. So there is no path with this current score 5. Right, now what I have to do, I have to decrease the score. Then actually it's possible that more edges will be present, will be considered. Right, here actually you can see that 4 will be discarded because it is the edge, the path will be stopped here there because the 4 will be not be considered in the graph. Clear? Now I will decrease the mid to suppose 3 in the binary search. Suppose I got 3 now. So in the 3, again I will start from here. So I will again start from here. Actually 7. Okay, now our mid is actually 3. Can I actually consider this edge? Yes, 7 is greater than or equals to 3. I can consider. Okay, next is this. This is 5. Yes, 5 is greater than or equals to 3. This will be considered. This edge actually I can take, but this the total cost in this path is exceeding k, so I have to stop here. Okay, next this path. Yes, 6 is greater than or equals to 3. Okay, I can take this. Again 4. Yes, 4 is greater than or equals to 3. I can take this. So this is 10. Still it is okay. Next is this edge. Can I take this edge? 2 less than 3. I can't take this, so I have to stop here. Got it? The intention and the flow, how it's working, it is clear. So you found this useful, please like the video. So what are the steps we have to follow? So first of all, discard all the edges where any node is offline. So this ensures the first condition to be a valid path. Correct. Next condition, what I have to do? So by using the remaining edges, the valid edges, I will create the graph. Now I have to use the binary search. Correct. So binary search, what I have to do? By using any mid score, I have to check that is there any valid path or not. Correct, to reach from 0 to n-1. So to check that is there a valid path or not, we can actually use many. This step is actually clear, right? Now I have to valid to the path. We have to get any valid path. So to check that any valid path or not, we can actually use many approach here. So diastra is one possible. Then actually we can use the DP, like, because this is actually directed acyclic graph. Okay, so DAG ultimately. So that means we can actually topo sort. Actually I am using the topo sort. Then we can actually we already have ordered the nodes. Okay, and this is always, we know the starting node is actually 0 and the destination node is actually n-1. So I'll check that if I start from here. So I actually have the topo sort, the topology order of the nodes, of the online nodes. Okay, then what I'll do, I will check that if I like from each adjacent node, I'll check that what is the node actually I can go from U to V. I actually have the adjacent list. Then actually check that what is the I can actually from U to V, this edge actually I can take or not. I'll actually add this in the current graph or not. Why I actually have to check that? Because I have to ensure that the score should be greater than equals to mid. Right, that means cost should be greater than equals to mid. Right, then actually I can only add. So that's why I have to check that the cost is greater than equals to mid or not. Then actually I will go to the V. Right, so I'll check that what is the minimum or minimum total cost to reach to V from 0, ultimate from 0, because I am starting from 0. So it will initially the distance will be 0, and I will check that from in the topological order that from this is suppose the current node is U. So how actually I can go. So I actually have some cost. So I'll check that can actually take this edge or not. So if I can actually take this edge in the current graph, then what I have to check that what is the distance, what is the total cost. So what I have to do, so cost of U, actually I know what is the cost of U. and I know that what is the current cost for this edge, and if it is less than cost of v, then this is actually optimal path, because ultimately our goal is to take maximum number of actually, or total cost should be less than equal to k. So somehow we have to optimize the total cost. So that's why I'll check that the cost of u, I know the cost of u because I am trying to jump from u to v. So what will be the cost for v? So it will be cost of u plus the cost of the current edge. So if it is less than the current cost actually I have in the node v, okay, if it is less than that, so this is the optimal path, right? So I will actually modify that. Cost of v will be modified with cost of u plus cost. Clear? So in this way I actually check that ultimately what is the cost for, so I'll check that what is the total cost for n minus 1. If it is less than equal to k, I have to return true. That means if it is less than equal to k, that means we actually have some valid path who actually the total cost is less than equal to k, and all the edges actually I have considered in the current path or in the current graph, that actually is greater than equals to the mid. Correct? This is clear how actually optimize this and how actually solve this problem. So if any suggestion, you will comment on that. Now go to LeetCode. So I actually have some edges, it may be valid or invalid, and we actually have the vector of online nodes and the k. So first of all I will check how many nodes are present. So I will get from the online node size. So first of all we have to make the adjacent list of all the nodes. So that's why I have taken a 2D vector, a pair. Why actually a pair? Because this is weighted graph, you can really say, because one will be the destination and the weight of the current edge or the cost of the current edge. So that's a pair, the v and the cost of the current edge, and adjacent of n nodes, because n nodes are still present, and I have to do the topological sort, right? So that's why I have to take the in degree. So for n nodes are still present, initially in degree is 0, and now here actually I have actually optimized this more, because I know in the during the explanation I have explained that the maximum the range of the cost, it can be 10^9, but I actually I have optimized that because the maximum cost can be hooked into the maximum cost. So what is the maximum cost is present in the graph, in the input graph, that will be the range. So that's why I have optimized this by using taking another variable max cost. The initial is 0, and the weight of the cost of the each edge I will compare that this actually make it one of the maximum cost or not. Okay, so ultimately this will be your range, the right range, maximum range. Got it? So I'm just returning all the edges. Okay, I will actually have three things. One will be the u source, v is the destination, and weight or the cost of the current edge. So this edge will be only considered, like initially I have actually explained that I at the beginning filter out all the offline nodes. So that's why I'll check that if any one of the node u or v is offline, that means false. So don't add this or don't consider the current edge, because ultimately this node will not be considered. So ultimately I have always honored this first condition. This is clear. Now that we are coming to line number 35, that means we actually all the nodes actually are online. So this is actually valid edge. So that's why just add into the for the u store v and the cost of the current edge. Got it? And also compare the maximum cost, because it will help me in the future to optimize the range search scope, and also increase the in degree of the v, because this is directed graph. So u to v, so in degree of v will be increased by 1. Clear? So after this for loop I actually have the all the little modified graph, like the edges or actually the all the nodes actually online, and I actually have the in degree of that all the nodes. Now to do the topological sort, what I have to do, first of all store only in the queue, store only the nodes actually the in degree 0, that should be the starting node, right? So that's a store. I'll check that the in degree of current node I is equal to 0, then it will store this. Okay, now I'll iterate till actually our queue is not empty. What I have to do, I actually iterate the adjacent list of the current node, and I actually decrease the in degree, right? You all know about the topological sort. So if it is in degree of the v, or from u to v, I am iterating the adjacent list of u. So like you can see that first of all pop the first node present in the queue. So this is actually u, and this node will be stored in the topological vector, that is to store the nodes, all the nodes in the topological order. Okay, and now actually iterate the all the adjacent nodes of node u. Okay, so first of all decrease the in degree of the node v, right, u to v. So here actually I have actually pair, first is the v and the next is the cost. So v dot first is actually the ultimate node v. So first of all decrease the in degree. If the in degree of that current node is equal to 0, that means this will be the next node in the topological order. So I'll store into the queue. Okay, whenever actually the in degree is 0, that means we actually consume all the actually edges that will coming to this node, current node v, correct? So I'll store this into the queue. Okay, so after this while loop, I actually in the vector topo order, I actually have all the nodes in the topological order. Clear? Now what I have to do next step, actually I have mentioned that I have to do the binary search. So I have to take two pointer, one is the L is starting with 0, and R, here actually you can actually take the 10 to the power 9 also, and here actually I have optimized this with maximum cost in the graph, input graph, and initialize the answer with -1, because they mentioned that if there is no head path, that means this if is always false every time. So that means that time I have to ultimately return the -1. So that's why I will initialize with -1. Got it? So this binary search will this value will run till our left pointer is less than equal to R. So for this current L and R, I'll get one mid. So what I have to check? I have to check that with this current score mid is in a valid path, whose actually the total cost of the path is less than equal to k, and the score is mid. That means that every cost in the graph or in the path is greater than equals to mid. Then actually I can actually consider. So if it is true, if it is written true, so that means we actually have some valid path using this current score mid. So I'll actually modify the answer variable with mid, and next our target is to maximize the score. So that's why I am shifting the left pointer to the mid -1, mid plus 1, because it may actually give us the mid, the next mid value will be more than the current mid value. So this may possible that in future actually I will get actually maximum answer. So that's why I'll shift the left pointer to the mid +1. Else I have to decrease the right pointer to the mid -1. Why mid -1? I have already explained. Because I have to, because the current score with the current mid, it is not possible to get a valid path. So that means we have to add more edges in the current graph. Then actually it is possible to get a valid path. So that's why shift decrease the range. So when actually it will decrease the range, decrease the score if it is shift the right pointer to the mid -1. Got it? And ultimately return the answer variable. So now see this helper function, or it will return true or false to get any valid path. So first of all, I will take one distance vector of size n, initialize with long max. Okay, and they mentioned that we have to always start from 0 and we have to reach n-1. So the distance of node 0 will be 0, because I am starting from node 0. Now I actually have the topological order of the nodes in this vector, right? So in this order actually I will actually iterate the all the nodes. Okay, and I'll check that if distance of the current node u is greater than k, that means this is not possible to go to further any adjacent node, correct? Because the total cost should be less than equal to k. I have already exceeding the range, or exceeding the k value k. So that's why it will not possible to go further any other nodes from any other adjacent nodes. So that's why I'll continue, go to the next node. Got it? If it is less than equal to k, that means we can actually have some option, right, to go to the other node. So that's why I will run the adjacent list of the current node u. Okay, so what will I get for this current node u? I actually have two things adjacent list. One will be the v, the next node I can go, and the cost of the current node from u to v, current edge, cost of the current edge. Got it? That will be better. So actually I can actually add this current edge in the graph, in the current path. What actually I can add? I can only add if the cost is greater than equals to mid. Why if it is less than mid? Why actually I will not add this into the current path? Because it actually decrease our score, but our score actually should be less, minimum mid, right? I am assuming that the score is mid. So if any one of the cost is less than mid, so then in this current path, if it is suppose valid path, so that time I will get the score I will get that will be less than mid, that will actually invalidate this path. So that's why I will only consider a path that actually the cost of the current is actually greater than equals to mid. Clear? So if the current cost of the current edge greater than equals to mid, then actually I can actually traverse the current edge. And when actually I go to the next node B, if it is, this will give a optimal. When actually optimal, so that means total cost. So distance of U, the cost or the total cost till U and the current cost C, if it is less than the total cost till V, actually I have seen till now, then actually this is an optimal path, right? So then actually if it is less than the distance or the total cost till actually V, actually I have seen till now, then actually modify this path, distance of V equals to distance of U plus C. Clear? So after this for loop, I actually have the distance, this vector, or actually I know that what is total cost from 0 to any node. Like I actually have that. Suppose there are actually 5 nodes. So 1, 2, 3, 4, 5. So I know the distance of 0 will be 0, and this is suppose x1, x2, x3, x4, x5. I know that from if I start from 0 to reach this node, what is total cost? This is x1, and if I start from 0 to reach here, the total cost is actually I actually have seen minimum total cost, it is x2. Similarly for to reach here, I actually minimum I have seen this is x3, this is x4, this is x5. So out of this, what is the minimum? So what I have to check that? I have to check that I have already validated the second condition, that all the total cost of path should be less than equal to k, right? And I have already validated that the score of this path will be equals to mid, because I have already considered the edges that actually cost is greater than equals to mid, right? So that's already validated. Now when actually I will get the valid path, so I will see that can actually reach this in node n-1 with less than equal to k, total cost is less than equal to k. That means I have to check that x5 is less than equal to k. If it is less than equal to k, so this is a valid path, so I'll return that. Clear? Return true. So that's why ultimately I'll check that after checking all the actually iterating all the actually nodes, the adjacent list and in the topological order. So I'll see that ultimate the distance or the total cost, actually I have added the node n-1 if it is less than equal to n, less than equal to k. So that means this I will get a valid path with the current score. With the current score mean actually mid. Got it? So return true, else return false. Clear? So if it is true, that means this is one possible answer. So I'll modify the answer. Answer will be mid. Got it? I have shared this code in the description. You can check that. I hope if you found this video useful, and like the video and subscribe channel. Thank you.